Hey, Bengals. Today we're going to kind of review some sixth grade skills about forces, pushes, and pulls. So go ahead and pause the video while you get your notebook ready and some pens or pencils so you can write down all of the information. All right, recall from sixth grade the definition of a force is a push or a pull. Any push or pull is a force. Forces can be applied by direct contact when things touch, such as friction. Like if you try to roll a soccer ball across the grass rubs against the soccer ball and slows it down. That's friction. Or if you're riding your bicycle and the wind is blowing against you, that's air resistance. Or they could just be forces applied by physically pushing or pulling on something, like when you're playing tug of war or football. The forces can also exert a force when they are not touching. In the case of gravity, gravity is a force that's pulling on you, electrical forces and magnetic forces. Okay, so forces are represented or shown with arrows, and we call these arrows vectors. Vectors show you the size of the force and the direction of the force. So if you look at the picture here, we have 1 Newton of force, and it's got a small red vector, and then 2 Newtons of force has a larger red vector because it's more force. Okay, forces are measured with a spring scale, and the spring scale measures in units called newtons. And that's why we put the N at the end there, like 1 Newton of force or 2 Newtons of force. So the combination of all the forces that are acting on an object is called the net force. So you can picture a net going all around something. It's a combination, all of the forces around it. That's the net force. Okay, and forces act in pairs. And so we sometimes try to find the net force. And if forces are helping each other, we're going to add them. So if both forces are pulling to the right, we would add them together to know the net force pulling on the right of an object. Okay. When forces are acting against each other, we subtract the amount of force to find the net force. So if Coach Uribe is pushing one way and Coach Hines is pushing another way, and they're working against each other, we're going to subtract their force to find the total force acting on the object that they're pushing. Okay, so if the net force is 0, then we say the forces are balanced. And in this case, there will be no change occurring, right? If it's balanced, there's no change that's going to happen. But if forces are not balanced, we're going to have a change. So unbalanced forces always cause a change in the motion. They can cause things to speed up or slow down or change direction, but unbalanced forces always cause some sort of change, and the object will move in whichever direction of the force is greatest. Okay, so here's some examples of balanced forces, right? A car just sitting in your garage, or a little kid sitting on the ground, or a cup on your table. But not all balanced forces are things that are perfectly still. Okay, look at the picture of the horse there, a horse galloping at a constant speed. That means that a speed that's not changing and moving in the same direction where it's not changing. That's actually a balanced force. Same with this motorcyclist. If the driver is moving at a constant speed, like 70 miles an hour, going in the same direction, that's a balanced force because it's staying the same. Unbalanced forces, on the other hand, are when one of the forces is larger than the other. Okay. And this will always cause a change in motion. Okay. It can change the position where things are located, the direction that they're moving, or the speed in which things are moving. Don't forget about gravity. Gravity pulls everything toward the center of the earth. Okay, and gravity is actually what determines your weight. Everything in the universe is made of mass or matter. And on Earth, we have a specific amount of gravity that pulls on our mass or our matter, and that determines our weight. Okay, on Earth, the force of gravity is 9.8 meters per second squared. You can find your weight by multiplying your mass in kilograms by the force of gravity. Now, if you go to the moon, the force of gravity is less. So you take your mass and multiply it by the moon's force of gravity, and you'll weigh less. Just like if you go to Jupiter, where the mass is, your mass will stay the same, but the gravity is greater. When you multiply there, you'll be very heavy weight on Jupiter. Okay. Something kind of funny I wanted to mention, right? Gravity pulls us down, but we just don't keep being pulled down until we're smashed into the earth, right? There's an upward force because remember, forces act in pairs. So there's an upward force that lets you stand up against gravity, and that's called the normal force. Okay, so the normal force is equal to the object's weight and it supports an object. Okay, so it's equal and opposite force of gravity. All right, if we want to overcome gravity like a rocket, right, we have to create a situation where we have unbalanced forces. That would cause a change. All right, so we're going to practice calculating the net force here a little bit. Take a look at these vectors. One is showing that there is a force of 15 newtons trying to move the box to the right, and then a force of 5 newtons also moving the box to the right. Okay, so in this case, they're working together, so we're going to add them to get the net force. So it's 20 newtons, and of course the box will move to the right. Okay, in this case, you can kind of picture there's a box and somebody's pushing on one side going to the left and somebody's pushing on the other side going to the right. They are certainly not working with each other, they're working against each other. So in this case, we'll have to subtract. So 10 minus 10 is 0. So that means these are balanced forces, they're equal. So is that box going to change what it's doing? No. So if it's just sitting there, it's going to continue just sitting there because these are balanced forces. Okay, another one. We have 30 newtons of force trying to push the box to the right, and we have 80 newtons of force trying to push the box to the left. Who is stronger? Of course, 80 newtons of force is stronger than 30 newtons of force. Since they are not working together, we're going to have to subtract. 80 minus 30 gives us 50. And since the 80 newtons was stronger to begin with and moving to the left, we know the box will move to the left. Okay, there are several others on your notes that I would like you to try and practice with right here, moving up or down. Okay, you can go through your slides and practice these on your own, right? Um, so be sure to take some time to do that so you get really good at calculating net force. And then when you are finished with these notes, you're going to go into Schoology and you're going to take the assessment. Okay, I'm going to do this last one with you here. It says we're trying to get the net force to be 30 newtons to the right, but we have up and down and side to side. So it's important that we work with opposite pairs, okay? So if we only want it to move to the right, we don't want it to move up and down, that tells us that we need our up and down forces to be balanced so it won't change moving up or down. So if I'm pushing up with 10 to make it balanced, I'll also need to push down with 10, right? And then I want the box to go to the right with 30 newtons of force, but somebody's already pulling to the left with 20 newtons of force. So how much force will I need if I subtract 20 to still get to 30? I would have to use 50 newtons of force. Okay, so when you're working with this, remember that our forces are going to act in pairs. All right, Bengals, good job. Go work on Schoology, and I'll see you again soon.